Well, I hope you're feeling the Beyonce theme for today, and now it's time to cruise right on into solving a real engineering problem using Mohr Circle. So I want to look at example 1 here. So example 1, we're asked to solve for the principal stresses and the maximum shear stress using Mohr Circle. And then for each case, determine the orientation of the element and show the stresses, the principal stresses and the max shear stress acting on that orientation. The stresses are on this element as shown. So remember, step 1 of our problem is to do any analysis that we need to figure out what is acting on our little block. So once we've done the analysis, we now have the stresses, the normal stresses and the shear stress. And again, we're dealing with 2D plane stress. So this is a plane stress problem with these stresses acting on it. Now, I've gone ahead and copied it up because I want to bring up our rules for Mohr Circle. So, when we developed our rules, we said the first step was to draw a sketch of the element. Boom, we have it done. So, I like to look at this and I like to identify the algebraic value of our stresses. So I see sigma x is in tension, so sigma x is a positive 12 KSI. Sigma y is in compression, so negative 2 KSI. And then our shear stress is up here on the x plane, positive y direction, so that's going to be a positive shear stress. So tau xy positive 10 KSI. Okay, so that's the first step. I drew a sketch of the element and I've identified all the stresses acting on that element. Next, I want to set up a coordinate system with sigma on the x-axis, positive to the right, and tau on the y, positive downward. So I've gone ahead and I have this kind of graph area. You can go ahead and plot your circle in underneath example 1. And we want to just make sure that we get all of our markers for sure. And we want to get sigma on the x-axis, tau on the y-axis, positive downward. All right, step 2 done. Step 3, plot sigma x, tau x, y. So we want to plot positive 12, positive 10. So I'm going to come into my coordinate axis. 1, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. You can go ahead and use the blocks to scale them. All right, so I need to plot 12, comma 10. 12, comma 10. So this is 2, 4, 6, 8, 10. 12, comma 10 is right about here. Next, I need to plot sigma y minus tau xy. So that's going to be negative 2, negative 10. I need to come into negative 2, and then negative 10. So that'll give me a point right up here. Then we connect the two with a straight line. Step 4, we solve for the center of the circle. So the center of the circle is right here. And we said that the center is equal to sigma x plus sigma y over 2, comma 0. So then our center is at sigma x, which was 12, plus negative 2 over 2, comma 0. So our center will be at 10 over 2, 5, comma 0. So my center, 5, comma 0. I can now draw the circle. So extending from 5. I always gotta psych myself up to draw the circle. How's that look? Maybe not the best circle. I'm gonna stick to it. All right, so we got something like this as a circle. 5, we want to use trigonometry to solve for the radius of the circle. So remember, this is my radius. Here's that inner triangle. This vertical distance is 10. This horizontal distance is 5 to 12. So that's 7. So my radius is equal to my radius squared equals 7 squared plus 10 squared. So that is 149. So I'll take the square root. R is equal to about 12.21 KSI. All right, I think that works out pretty good. That's step 5. So step 5 is a little bit easier to see when we have real numbers. Step 6, we want to identify the principal stresses and the max shear stress. So looking at my circle, I see that my principal stresses look like they're about here. I'll call this sigma 1. We'll call this value sigma 2. Remember, we said identifying this sigma 1 and sigma 2 is equal to the center plus or minus the radius. So in this case, that's going to be 5 plus or minus 12.21 KSI. This is in KSI as well, because they're all in terms of stress. So this gives us that sigma 1, 5 plus 12.21, 17.21 KSI. Sigma 2, 5 minus 12.21 gives me a negative 7.21 KSI. There we have our principal stresses. This is equal to 17.21. So it looks like I did pretty good drawing the circle there. This one's at minus 7. Not too terribly. Not too terrible. This is minus 6, somewhere between there. Minus 7.21 KSI. We also want to find the max shear stress. So the max shear stress is below our center, and it has a magnitude of whatever the radius is. Tau max equals our radius, which is equal to 12.21 KSI. All right, so I think we accomplished the first part of our problem, is that we wanted to solve for the principal stresses, and we wanted to solve for the maximum shear stress. The next part of the problem is to draw the elements at these orientations of the maximum principal stresses and at the shear stresses. So that'll be step number 7. So I'm going to come to my circle. I started at sigma x of 12, and I'm going to rotate on my circle counterclockwise through this angle that I call 2 theta p. So if I set tangent 2 theta p equal to opposite over adjacent, that's going to be 10/7. So then I have to solve for theta p. Theta p is going to equal tan inverse of 10/7 divided by 2. I can't do that in my head. I'll be back in 1 second. That's 27.50 degrees. So theta p equals 27.50 degrees. We want to sketch the element at this orientation. So my original element is like this, with an original x and y. I rotated on Mohr Circle counterclockwise, and so on this I want to rotate counterclockwise a distance of 27.5. And this is going to be the normal now to my principal plane. So we get something that looks like this. I rotate this block 27.5 degrees. Again, I'll grab my little block so you can see this. This was the initial block. We rotate counterclockwise 27.5 degrees, and this is the orientation on which we experience the principal stresses. Now, what are the magnitudes of those? Well, we said that on our circle, we go from this point, when we go counterclockwise, that brings us to sigma 1. So that means that sigma 1 is in this direction, has a magnitude of 7.21 KSI. And then that means on the other plane, we have sigma 2. Sigma 2 is actually in compression, so let me show that in compression. And it has a magnitude of minus 7.21 KSI. And so this is what the principal stresses look like on this block. Now we can repeat this for the shear stress. So we'll do that here in a second. I'm going to erase my work for the principal stress, and we'll do it for the shear stress. Now we're ready to do the work for finding the sketch for the maximum shear stress. So, coming from my point 1210 to get to the max shear stress, I need to rotate clockwise this value, which we said was 2 theta s. So, tangent of 2 theta s equals the opposite, which in this case is now 7, divided by the adjacent. So let's see, opposite is 7, adjacent is going to be 10. So now we can solve for theta s. Theta s will equal 17.50 degrees. This is also clockwise. If you want to write that, it's good practice so we know which direction to turn our block. So again, if we take our initial block with the initial stresses on it, and we rotate this 17.5 degrees clockwise, 17.5 degrees clockwise, we will get to this orientation which has the maximum shear stress acting on it. So I'm going to go ahead and sketch that block. This was the original X and Y direction. We rotate clockwise, theta S 17.50 degrees. To get to this block. And this block has the maximum shear stress on it. Maximum shear stress has a value of 12.21 KSI. And that would be positive on this face, which is going to be positive X. You can almost think of this as X prime, and our Y prime would be that way. So because this is a positive number, positive X prime, Y prime should be oriented like this. And then equal and opposite on the other side. So tau max, 12.21 KSI. Remember, on the max shear plane, we also have a normal stress. And so again, if we think about this, the coordinates of this point right here, our coordinates are going to be 5, 12.21. So this 5 is the value of the stress on this plane. And then we have the equal and opposite on the other side. So on the other face, sigma y, we also have 5 KSI, sigma y prime. And if you go back to our previous lesson, you'll know that we said that this value was sigma average, which is sigma x plus sigma y over 2, which is the center of our circle, or 5 KSI. So this is all coming together. Mohr Circle helps make that happen. And so hopefully you're able to follow this. This is always the hardest part, to visualize the stresses. But hopefully right now, on your first time through, you're confident you're able to solve for sigma 1 and sigma 2 and also tau max. And keep on practicing. We'll go ahead and do another problem soon. I hope you are enjoying Mohr Circle. I thought I could even draw these transformation equations for sigma x prime, stuff on these little circles. And you can almost think of these like, little halos, right? So you could say, I can see your halo, halo, halo. I can see your halo. Everywhere you're looking now, you're surrounded by Mohr Circle. I can see the circle and the stresses. I hope they will pray they won't fade away.